Imagine teaching a robot to walk across a room, not by showing it how you walk, not by describing physics equations, but by letting it try, fail, fall, wobble, adjust, and eventually glide confidently across the floor. This is the magic of policy optimization, one of the core ways intelligent agents learn to make decisions. It powers everything from game-playing AIs to self-driving cars to robotic control systems. In this episode, we go deep into what policy really means, why optimizing policies is so challenging, the brilliant ideas behind methods like policy gradient, reinforce, Actor-Critic, PPO, and more. Real examples you can visualize instantly, and how this shapes the future of AI agents you'll interact with every day. Let's unlock one of the most fascinating pieces of the RL universe. What is a policy? In reinforcement learning, an AI agent is constantly taking actions in an environment to maximize long-term reward. A policy is simply the strategy the agent uses to choose those actions. Think of it like a doctor diagnosing based on symptoms, a gamer deciding when to attack or defend, a delivery robot deciding which path to take in a crowded city. Technically, a policy is a function, the probability of taking action A in state S. Policy optimization means improving this function to maximize future reward. Simple idea, deep consequences. Why not just try every strategy? Because the space of possible policies is astronomical. Imagine asking, let's test every possible way a robot could move its joints in every scenario. You'd need more time than the age of the universe. So instead of searching brute force, we optimize the policy step by step. This is where policy gradients enter the picture. Policy gradient intuition. A policy gradient method directly adjusts the parameters of a policy network to increase expected reward. Think of it like adjusting the knobs on a musical equalizer, but instead of making audio sound better, you're making decisions smarter. The key idea: if an action leads to higher rewards, make the policy more likely to choose it again. The technical formula, meaning, look at actions the agent took, see the reward it got, increase the log probability of good actions, decrease the log probability of bad ones. This forms the backbone of algorithms like reinforce. Reinforce explained with a simple example. Imagine training a drone to reach a target point. It starts with a random movement policy. It tries a trajectory. If the final result is good, we reinforce that behavior. If it's bad, we reduce the likelihood of that behavior. The algorithm only needs the actions taken, the total reward. But it suffers from high variance, slow learning, no baseline for comparison. This leads to the next breakthrough: Actor-Critic. Actor-Critic. Two brains are better than one. The actor is the policy network. The critic is a value function that evaluates how good a state or action is. Actor. I think this is the right move. Critic. Actually, that was a bit worse than expected. Adding the critic gives lower variance, more stable updates, faster learning, better credit assignment. Mathematically, it uses the advantage function, meaning, was this action better or worse than what we thought? Proximal policy optimization, PPO, the gold standard today. PPO, developed by OpenAI, revolutionized policy optimization by solving one big problem. Taking steps that are too big breaks learning. Taking steps that are too small wastes time. PPO introduces the clipped objective. This prevents huge updates to the policy. Think of it as safe learning, like allowing the agent to explore, but never too far from the known good strategy. Why PPO is loved. Stable, efficient, scalable, works beautifully in complex environments. It powered advancements like robotic locomotion, game-playing agents, simulation-trained robots transferred to real world. PPO is the backbone of many modern RL achievements. Real-world applications. Autonomous vehicles. Cars use policy optimization to decide when to brake, when to accelerate, how to navigate safely. Robotics. Manipulation tasks like picking objects, balancing, using tools. Finance. Optimizing trading strategies based on state transitions. Recommendation systems, where long-term user engagement matters more than one click. Game AI. Agents learning strategies dynamically rather than scripted actions. Where policy optimization is heading. We are entering an era where AIs won't just classify or predict, they will act. Policy optimization is the foundation of autonomous decision-making systems that improve through experience. Whether it's a robot walking, an AI flying drones, or algorithms optimizing global logistics, policy optimization is the quiet force shaping the future. What if our everyday tools could adapt their behavior like this? That's the future we're building toward. See you in the next one.